Okay, so the remainder of the class, we'll hear from Mark Kamiankowski, who's going to tell us about using the polarization of the cosmic microwave background to search gravitational waves in the ELF band, the extremely low frequency band. Mark, as you know, is a professor here at Caltech. He is responsible, together with colleagues, for the idea that you might determine the geometry of the universe, whether it's flat or not, using the so-called Doppler peaks in the intensity pattern, or the correlations you see in the intensity pattern of the cosmic microwave background. That's been done successfully. And so now he's also proposed the idea of using the polarization patterns in the microwave background to look for the gravitational waves in the ELF band. And I'm sure that will also be done successfully, and you'll tell us how.
Well, you're confident. Okay, so those are transparencies I'm not going to show, but they've got numbers on them that I might have to refer to. So I'm not really sure where to start. Should I start with the cosmological setting, or should I just start with some equations? I'll start with the cosmological setting. I don't have a whole lot of equations. So, we live in a universe that's about 15 or so billion years old now, maybe 13, 14 billion years old. We're not really sure. And when we look out in the sky, in every direction, we see radio frequency photons coming at us. So these are on order 100 gigahertz photons. They have a perfect black body spectrum. And we are quite confident that they were produced shortly after the Big Bang, about 400,000 years after the Big Bang. And therefore, that when we look in a given direction in the sky, we're actually seeing, when we look in a given direction, we're seeing, say, 15 billion light years. 15 billion is 1.5 times 10 to the 10 light years. In that given direction, we're seeing photons emitted from some point in the universe over there. And when we look in this direction, we're seeing photons emitted from this point over here. So that when we look at the cosmic microwave background over all 4 pi steradians of the sky, we're looking at a spherical surface. Now, since the spherical surface has a radius of 1.5 times 10 to the 10 light years, it's the farthest that we can possibly see. And we believe that the photons are coming from the time at which the universe first combined hydrogen atoms, in which electrons and protons first combined to form hydrogen atoms. So during the first 500,000 years of its lifetime, the universe existed at very high temperatures greater than electron volt. So electrons and protons wouldn't exist as bound atoms because a photon would come along and dissociate it. When the temperature of the universe cools below about 10 electron volts, electrons and protons can combine to form hydrogen. In the early universe, if there are a whole bunch of free electrons around, then a photon can scatter from an electron. But after the electrons and protons combine to form hydrogen, low energy photons with frequencies below the few electron volts at which it can scatter resonantly from a hydrogen atom, at lower frequencies, the photon just sees a neutral particle, doesn't couple to a neutral particle, and therefore it propagates freely. So the photons that we see in this cosmic microwave background came to us from a time when this process occurred, which is about 500,000, 400,000 years after the Big Bang. And the strange thing is that the temperature of these photons, the intensity of the radiation, is the same in every direction on the sky to 1 part in 10 to the 5th. And the reason this is strange is because when these photons last scattered, the universe is 400,000 years old, so the size of a causally connected region had to be something like 400,000 light years. And today, the universe is about 15 billion years old, so the size of a causally connected region is much larger. The thing is that when these photons last scattered or were produced over here, and when they were produced over here, there was no way that this part of the universe could have been in causal contact with this part of the universe. The causally connected region was very small. And if you actually take 400,000 divided by 15 billion and take into account the expansion of the universe has expanded by about a factor of 1,000 since the time these things expanded. What you find is that this causally connected region subtends an angle of roughly 1 degree on the surface of the sky. Okay. Now, there are 40,000 square degrees on the sphere. 4 pi steradians is equal to 40,000 square degrees. And that means that when we look at this cosmic microwave background, we're looking at 40,000 causally disconnected regions. But each of them has the same part to 1 part in 10 to the 5th. And this gives rise to the causality problem, or horizon or homogeneity problem, which is how did this region of the universe know to have the same temperature as this region to 1 part in 10 to the 5th? Okay. Now, the best explanation for this, by far, actually it's the only real good explanation that we have, is inflation. And inflation works more or less like this. So suppose I plot here the physical size of something that's expanding with the universe, and I plot over here the scale factor, A, of the universe. If I'm looking at some co-moving distance, so if I'm looking at, say, 2 galaxies that are very far apart and each of them is moving in expansion, the physical distance between them scales linearly with the scale factor. Okay. So I can draw the size of various, the physical size of various co-moving distances, and these are small objects, or small distances, and these are larger distances. Now, in the standard Freeman-Robertson-Walker cosmology, we live now in a universe that's matter-dominated. And during matter domination, there's a Friedmann equation that relates the expansion rate of the universe, h, to the density of the universe and Newton's constant. You guys know the capital G is equal to the Newton's constant, right? Okay. That's what I was going to say.
Can I ask why it's matter dominated? Because there's not enough matter to close the universe.
Well, today there's not enough matter to close the universe, but at redshifts of, say, 3 or bigger, the universe would have been was matter dominated.
Okay. It's matter dominated in the sense that matter dominates over radiation. It doesn't mean that. Okay. It doesn't refer explicitly to whether the universe is open or not.
Yeah, that's true. So, I mean, there is another term here, a curvature term, but let's think about that for now. Okay. So during matter domination, the density decreases 1 over the scale factor cubed. So h is proportional to 1 over a to the 3/2, and h to the minus 1 is proportional to a to the 3/2. Before radiation domination, at redshifts greater than about 10,000 or so, actually about 3,000, the universe was 1/3000th of its present size, and earlier the universe was dominated by radiation. The energy density in radiation decays as 1 over a to the 4th, which means that h to the minus 1 is proportional to a squared. H to the minus 1 is the Hubble distance, which is roughly speaking the farthest distance that we can see. Okay. Now h to the minus 1 grows either during matter domination or during radiation domination more quickly than the physical size of any given object or any given co-moving scale, which grows as a. So that means that during matter domination, things look, the horizon grows maybe sort of like this. During radiation domination, it's a little steeper. And the way inflation works is inflation postulates The way that inflation works is that inflation postulates that at some point in the early universe, there was a scalar field, phi, which could be, say, a Higgs field associated with grain unification, or a dilaton field, or a scalar field that shows up in Petchy-Quinn symmetry breaking. We don't know, but some scalar field, phi, that has a potential energy density, V of phi, and it could look like this, or the potential energy density could look something like this. All we have now are essentially toy models, so either of these will work. And all we require is that at some point early in the universe, the scalar field is displaced from its minimum and is slowly rolling towards the minimum of its potential. So if the energy density of the universe is dominated by the vacuum energy density associated with the displacement of the scalar field from its minimum, then at that early time, the energy density of the universe will be approximately equal to V of phi. And if phi is rolling slowly, and heuristically you could see that it would roll slowly if it's, say, near a flat part of the potential. If phi is rolling slowly towards its minimum, then V of phi remains roughly constant. So if V is roughly constant and the energy density is proportional to V, then at this early time, h squared, which again is a dot over a, is proportional to a constant, which means that a has a solution which is proportional to e to the ht, with h roughly constant. So during inflation, h is roughly constant. The scale factor grows exponentially, and a constant scale factor looks something like this. And we suppose that there might be some pre-inflationary epoch here. We'll not worry about that. So this region here is inflation. This region is radiation domination, and this region is matter domination. So the interesting thing about inflation that distinguishes it from matter domination and radiation domination is that during radiation domination or matter domination, the Hubble distance, which is roughly speaking the furthest that we can see, grows more rapidly than the expansion rate, than the scale factor grows. Whereas during inflation, the scale factor grows more rapidly than the horizon, or the Hubble distance. So, in a radiation-dominated or matter-dominated universe, the Hubble distance is growing more rapidly than the scale factor, which means that at later times, there will be more and more things coming into the horizon. Okay, later times we'll be able to see further and further. So if today we can see 10 billion galaxies, in the future we'll be able to see 20 billion galaxies, 50 billion galaxies, 100 billion galaxies, etc. Our Hubble volume, our co-moving Hubble volume will increase. Okay? So in other words, during radiation domination or matter domination, information is coming into our Hubble volume from outside the horizon. Okay? On the other hand, during inflation, co-moving scales are exiting the horizon. So if we were living in a universe that was inflating, then things that we see now, we would be unable to see in the future. So if the universe has 10 billion galaxies within our Hubble volume today, in the future it'll be 5 billion, 2 billion, 1 billion. So during radiation domination or matter domination, information and objects enter the horizon, and the universe becomes increasingly complicated. Whereas during inflation, information and objects exit the horizon, and the universe becomes increasingly smooth and simple. So if the universe is inflating, if we live in a universe that's inflating, then there's a horizon that surrounds us that acts a whole lot like a horizon that surrounds a black hole. Except in this case, we're inside the horizon, whereas with a black hole, we're outside the horizon. So if the black hole has an event horizon, you throw objects in there, and they disappear forever, and you can never see them again. In an inflationary universe, there's a horizon that surrounds us, and if you throw an object outside that horizon, it disappears, and we never see it again. And there are actually cosmic no-hair theorems for an inflationary universe that parallel those for black holes. For a black hole, you know that if you wait long enough, the black hole eventually settles down classically to a state that's described only by a mass, a charge, and an angular momentum. And likewise, if you stick around long enough in a universe that's inflating, with time, everything disappears beyond that horizon, and you're left with a universe that's completely empty. So, inflation is a mechanism that can smooth the universe. In more concrete terms, the reason that these two causally disconnected regions of the universe can be in causal contact, or put in causal contact in inflation, is that if we look at this diagram over here, so this is today. So we live sometime over here during matter domination, and there is some scale, co-moving distance scale, that is just entering the horizon today. So the co-moving distance that separates this point from this point over here is going to be denoted by this dashed curve over here, dashed line over here. And this is the scale that is just entering the horizon today. This is the distance that's just entering the horizon today. During this period of, during this part of the history of the universe, during matter domination and radiation domination, the scale is well outside the horizon, which agrees with what we said before. It was not in causal contact. But if we go sufficiently far back in the past, and there was an inflationary epoch, at some time sufficiently far back in the past, this co-moving distance was inside the horizon. So if we have inflation, we can take some distance scale that's initially inside the horizon, blow it up outside the horizon, and then we'll come back inside the horizon later on during matter domination. So what we do in inflation is we take this huge region, we put it into a very small, causally connected pre-inflationary patch, which then gets blown up exponentially, and this exponential expansion to turn into a universe that's big enough for us to see. Big enough to be encompassed in the universe that we see. So, inflation, as I've told you now, is an interesting idea and sort of religion. But it has a number of interesting properties. First of all, inflation predicts that the universe is flat. And the reason inflation predicts that the universe is flat is that we start more generally with the Friedmann equation that's looks something like this. So up here I neglected this curvature term, but more generally if the universe is open or closed, the Friedmann equation contains, in addition to this density term, a curvature term which can be plus or minus 1 over a squared, depending on whether the universe is open or closed. Now suppose that the curvature term is non-negligible initially. So suppose the universe begins and it's open or closed. And in that case, we would expect this term to be roughly comparable in magnitude to this term over here. But during inflation, A is proportional to e to the ht. the scale factor grows exponentially, the energy density remains roughly constant during inflation, but this term over here, the curvature term, e to the minus 2 is proportional to e to the minus 2 ht. So if this term is comparable in magnitude to this term over here, then after a sufficiently long period of time, it will become exponentially small compared with this term over here. So inflation in this way predicts that the universe is flat. You can actually be more quantitative. You can actually show that if you have enough inflation, if there's enough time lapse between this time at which the current horizon exits the horizon during inflation and the end of inflation, then this term will be very, very small compared with this term today. So the universe should be flat according to inflation. Now the other elegant prediction of inflation, yeah? Yeah? Okay, do I stop?
Yeah.
Okay. Okay. So one of the very interesting things about inflation is that it predicts a nearly scale-free spectrum of density perturbations and of gravitational waves. And I'm not going to get through the entire derivation, but I can tell you more or less what goes on. You know that if you have a black hole, classically it's described by only 3 parameters, which are the charge, mass, and angular momentum. But you know that quantum mechanically, there is Hawking radiation emitted from the black hole. Okay? So if you study quantum mechanics, say of the electromagnetic field, in the presence of a Schwarzschild spacetime, you will find that if you are an observer at a large distance from the black hole, you will actually see a black body, the black hole will appear to be emitting a black body spectrum at some temperature. And the temperature is inversely proportional to the mass. Is it mass or mass to the 2?
The mass.
Right, okay. It's inversely proportional to the mass. And the reason that makes sense is because it's actually the curvature of space-time that's giving rise to this effect. And if the mass is bigger, then the curvature at the horizon is smaller. If the mass is smaller, then the curvature of the horizon is bigger. So, classically, things fall into the black hole event horizon, but quantum mechanically there's a spectrum of radiation emitted from it. In inflation, we have a horizon that's surrounding us, and classically things fall beyond that horizon, never to return. But quantum mechanically, there's radiation emitted from that horizon in the exact same way that there's radiation emitted from a horizon of a black hole.
But the horizon of the logical horizon should have a very, very small coverage of the radiation.
Not necessarily. Well, let me write it down. Well, I'll answer first. The curvature during inflation can be quite big. Actually, it's a very good question. The curvature during inflation can be very big. And the reason is that inflation is thought to occur when the energy density of the universe is comparable, say, to the gut scale energy density. The curvature is probably comparable to a black hole, to the curvature you get at the Schwarzschild horizon of a black hole with the mass maybe of a few thousand Planck masses. Okay. If inflation takes place later at lower temperatures, then the energy density of the universe will be smaller. The curvature during inflation will be smaller, and the resulting gravitational wave or radiation production will be smaller.
I see. So this horizon ends up being really smaller in the universe. Yeah, that makes sense.
Yeah.
Now, question. This cosmological horizon is an observer-dependent quantity. Like, if I sit here in the universe, my horizon will be somewhere around here, and if you sit right next to me, your horizon will be centered on you.
Right.
So my horizon will emit gravitation, will emit the Hawking radiation. and see it, and your horizon will also emit Hawking radiation. So is this Hawking radiation being generated all over spacetime?
Well, yeah, that's also a good question. So if you actually look at the calculation of, if you actually look at how, if you go through the steps that tell you that there's Hawking radiation coming from a black hole, the strange thing about it is that you can convince yourself that if you're at large distances, asymptotically large distances, you'll see black body emission from the black hole. If you're slightly closer, you'll see some black body emission at a slightly different temperature. The thing is, if you look at the actual mathematics, there isn't a point from which the radiation is being produced. It's one of these very unusual, it's an unusual consequence of quantum field theory and curved space-time. You can show that any observer in an inflationary universe will see a black body spectrum of radiation, but they won't be able to say where exactly the radiation is being produced.
Isn't it that any observer is going to say that the radiation is being produced from itself?
Yes, everybody will think that it's coming from a horizon around them.
Why don't we let Mark go on? We want to get to the gravitational waves.
Really? Okay. Okay, so the space-time metric of an expanding universe can be written as a squared of tau times minus d tau squared plus dxi dxj, where tau is the conformal time. So usually you see this written as minus dt squared plus a squared of t dx squared, but if you make a change of variables to the conformal time, then it just looks like a flat space-time with some scale factor that depends on the conformal time. If now, sorry, there's a delta ij here, I forgot to write, that multiplies this. If now I allow for the possibility that there could be tensor perturbations to the space-time metric, then the most general metric with tensor perturbations will look like that. Actually, trace-free, symmetric trace-free tensor perturbations, okay, which are gravitational waves. So if the universe isn't expanding, if I live in Minkowski space, then A is just 1, and then this just looks like the ordinary metric that you write down for gravitational waves. With an expansion of the universe, I get something like this. I can plug this into the Einstein equations, and if I plug this into the Einstein equations, I get an equation for this E, ij, which looks like this, where h again is the expansion rate, a dot over a, although that dot over there is a d by dt, and this one is a d by d tau, to a h eij d dot plus k squared eij t, and the right-hand side is the source term, which is 8 pi g a squared times the pressure times an anisotropic stress. In a vacuum, this is right-hand side is just 0. So if I use more conventional or familiar notation, I can redefine E in terms of an H being the scale factor times E, and then what I'll find is that H satisfies an equation that looks like this. And this is just the wave equation.
So K is a co-moving wave vector?
Yeah, thanks. So K is a co-moving wave vector. And this is just an ordinary wave equation. So if the universe is not expanding, if I live in Minkowski spacetime, then A is just a constant, H is 0, and I just have d by dt squared plus k squared h is equal to 0. So actually, I forgot to... This is the... I did do something that I didn't say. So first I change... Oh, I already did it up here. This is the Einstein equation for a particular Fourier mode of the tensor perturbation. I neglected to say. So actually, what I should have, if this was actually the Einstein equation, I would have a minus del squared over here. But if I consider a particular Fourier mode of the tensor perturbation, then I get a k squared over here. So this is the equation of motion for a particular gravitational wave of wave number k in an expanding universe. And again, if there's no expansion, then h is 0, a is a constant, and I just get the usual wave equation. Now, with the expansion, there's something that looks sort of like a friction term over here, and with the expansion, the wave number is changing with time. Now, you can solve this equation. If you solve it in radiation or matter domination, if you solve that equation during radiation or matter domination, you get more or less what you would expect, which is that this gravitational wave propagates as it would in Minkowski space, but the wavelength changes as the universe expands. Okay? In other words, the wavelength of the gravitational wave redshifts. So, during radiation domination or matter domination, the solutions are propagating waves that redshifts. Whereas, if I look at the solutions during inflation, the solutions during inflation are different. During inflation, at very early times, let's see, h is roughly constant, a is growing exponentially. So at very early times, this term will be bigger than this term, and the waves will propagate as they do ordinarily. So in asymptotically early times, the waves propagate ordinarily. And actually, if you actually figure out what asymptotically early times means, it actually means, when you look more carefully, when the wavelength is smaller than the horizon. But at late times, okay, if we think again about a particular Fourier mode, the wavelength of this Fourier mode, so suppose we look at a Fourier mode with this particular co-moving wavelength, the physical wavelength of that Fourier mode is growing linearly with a scale factor. At early times, this wavelength of this Fourier mode is smaller than the horizon, and so this mode, the propagation of this mode really doesn't care about the horizon, and at these early times it propagates. However, at some point, the wavelength becomes larger than the horizon. And if the wavelength is larger than the horizon, that means that the crest of a particular wave can't see the trough of that particular wave. And therefore, that wave can't propagate because the crest and trough aren't in causal contact. And you can actually see that by looking at the solutions of these equations. So at late times, A is growing exponentially. At late times, this term here becomes negligible compared with this term. And the solution of this equation is h is a constant. Little h is a constant. So at late times, the amplitude h...
Still during inflation.
Yes, during inflation. Yes, late. Okay, they're still during inflation. H is like a constant, late times during inflation. Yes. So late times during inflation, H is roughly constant. And then at very late times, at later times when we get to matter domination or radiation domination, when this particular mode re-enters the horizon, then it propagates again like a gravitational wave.
The first term we looked at the geometric optics for gravitational waves. And this corresponds to the early times when it propagates freely, that's the geometric optics regime.
Right.
And the late matter-dominated or radiation-dominated regime, again, it's geometric optics.
Right.
And this period when H is constant, that's when geometric optics has failed.
That's right. Now, the reason this is interesting, and the reason why quantum mechanics comes in is the following. Classically, if we start with a vacuum, then we'll always have a vacuum. So classically, if I start with a vacuum, that means that there are no gravitational waves, which means that the amplitude H is always 0. So in a vacuum, the solution is H is equal to 0. Quantum mechanically, though, each of these Fourier modes, if the universe is not expanding, quantum mechanically, each of these Fourier modes satisfies the simple harmonic oscillator equation of motion. Right, this is just H double dot plus omega squared H is equal to 0. So each Fourier mode, the amplitude of each Fourier mode satisfies the simple harmonic oscillator equation of motion, and we know that the simple harmonic oscillator ground state has an amplitude H that is not equal to 0. So at very early times, even in a vacuum, there is a vacuum mode of H. H has a non-zero expectation value because of vacuum oscillations. And what happens is that those vacuum oscillations, at later times, when the wavelength becomes larger than the horizon, freeze out. So at early times, when the classical wave would propagate, the quantum mechanical mode behaves like a simple harmonic oscillator, which has a non-zero expectation value, even in the ground state. And at later times, this non-zero vacuum expectation value turns into a classical perturbation. So, in this way, one can have gravitational waves that are produced in a vacuum if the universe is inflated. And this directly parallels the calculation of Hawking radiation from a black hole. Now, without going through details, it's...
Let me just remark, in the Hawking radiation case, we know the input is vacuum, and the output is the thermal. In this case, we don't know enough about the Big Bang singularity to know that you got the gravitational field coming off in the vacuum.
Well, that's a tough question. There isn't an easy answer. The best answer is that suppose we're looking at things that are entering the horizon today. Okay, then those are all modes that have exited the horizon during inflation after this period over here. Now, if inflation actually looks like this, and there were, several hundred e-folds of inflation before the current horizon exited, then it stands to reason that anything that was there beforehand would have inflated away. So that even if the universe, over here, before inflation had stuff in it, by the time this mode exited the horizon, there were enough e-folds of inflation that most of the junk would have already exited.
That's a plausibility, right?
Yes. Well, let me tell you another reason why you should believe this. The same arguments that we use to predict the gravitational wave background, we also use to predict the spectrum of density perturbations. And although that's a crappy argument, the truth is we now have empirical evidence that something is producing a nearly scale-free spectrum of density perturbations that look a lot like those you'd expect from inflation.
I like that argument better.
And it actually works even better. So suppose there was some pre-inflationary chunk that didn't get redshifted away. That would show up more so here than over here. Okay, there would have been more redshifting, more times for that stuff to disappear on the horizon than over here. So if there was some pre-inflationary chunk that was still there, you would expect it to affect the largest scale fluctuations in the universe. And the fact that Kobe sees, and Kobe and Boomerang see a spectrum of density perturbations that's very consistent with flat on the largest scales, that also suggests we're on the right track. So it's not just that we see quantum fluctuation with a nearly scale-free spectrum, it's that on the largest scales, there is no apparent deviation. We couldn't say that a few years ago. It's good. So, the only thing that is affecting the production of these gravitational waves is this H over here, the capital H. And what you can show is that the little h the RMS amplitude of any particular Fourier mode, or any particular gravitational wave, is proportional to the energy scale of inflation divided by the Planck mass. Planck mass being 10 to the 19th GeV. So G is equal to that, and Planck to the -2. And H bar equals C equals 1 units, and G not equal to 1 units. So, squared. The reason this makes sense is that the only thing that's affecting the production or the excitation of those little h's there, of the amplitude of the gravitational wave, is the fact that H, capital H, is non-zero. During inflation, H is equal to 8 pi over 3 times the Planck mass squared times the energy density, which is V, all this to the 1/2. And V is a vacuum energy density. V is proportional to an energy scale of inflation to the 4th, and so this looks like an energy scale of inflation squared divided by Planck mass. And to get the units right, there has to be a Planck mass squared here. So that doesn't belong there. That belongs there. Okay. So the only thing the little h can depend on is big H, which can only depend on the height of that inflaton potential, which is what we call E inflation to the 4th, the energy scale of inflation to the 4th. So it doesn't depend on the details of inflation. It doesn't depend on whether there's a Pechi-Quinn symmetry breaking scale, or, sorry, it doesn't depend on the details of the physics. It doesn't depend on whether phi is part of an SU5 multiplet or an SO10 multiplet or a U1 multiplet. It doesn't depend on whether it's a dilaton or anything. It doesn't depend on the shape of this potential. All it depends on is the height of this potential at the time that inflation is occurring. So the amplitude of the gravitational wave background predicted by inflation looks something like that. Now I can actually show you a more detailed prediction. This is actually the primordial spectrum. Sorry?
Do you want to follow ahead?
No, no. I most surely do not want an overhead projector. I want my graph that has the numbers. Okay. So here it is. So, I just want the numbers. This is actually the primordial spectrum. So this is the amplitude of the gravitational wave when it enters the horizon. After the gravitational wave enters the horizon, the amplitude will decrease because of the cosmological expansion. There will be a redshift. Okay. And if I make a plot of the dimensionless amplitude h as a function of the frequency, nu, in hertz, at scales that correspond to the current horizon, 15 billion light years. I guess this is a frequency, so it's actually h, not h to the minus 1. In terms of the horizon, at the horizon, E inflation squared divided by m Planck squared reaches its maximum value. And then at higher frequencies or smaller wavelengths, this decreases like so, and then it decreases slightly less steeply. Now the break over here is due to the fact that this is the wavelength that enters the horizon during the break between matter radiation and radiation domination. So these modes here are sufficiently large that they enter the universe after the universe has become matter dominated. These wavelengths over here are sufficiently small that they enter during radiation domination. So these are the modes over here. These are the wavelengths that enter during radiation domination. And then the break occurs for the wavelength that enters the horizon between matter domination and radiation domination. And the break in the slope is due to the fact that the redshift is different during radiation domination and matter domination. Okay. Now, if I draw an expected sensitivity for LISA on here, LISA looks something like this, and LIGO looks something like this.
A little optimistic for LISA.
Okay. Well, yeah. So let me say, the fluctuations, the gravitational waves at the largest wavelengths, wavelengths corresponding to the horizon today, can produce temperature fluctuations in the cosmic microwave background. So there will be temperature fluctuations in the cosmic microwave background that are proportional to h, which means that they're proportional to E inflation divided by m Planck squared. And we know from COBE, from measurements of the temperature of the cosmic microwave background, that the temperature is very uniform in all parts of the sky to roughly 1 part in 10 to the 5th, at least. So we know that this has to be less than, say, 10 to the minus 5, which means that E inflation divided by m Planck has to be less than or approximately 10 to the minus 2.5, or that the energy scale inflation has to be less than about 3 times 10 to the 16th GeV, since m Planck is 10 to the 19th GeV. This very stupid, boneheaded calculation actually gets the right answer, although It's probably like the homework problems I grade sometimes when the answer's in the back of the book. Any line of reasoning leads to the right answer when you know it. So, but otherwise, we don't know what the energy scale of inflation is. It has to be less than 3/10 of the 16 GeV to be consistent with COBE, but we don't know what the energy scale of inflation is. If inflation had something to do with grain unification, then you would expect this E to be something like 10 to the 15 or 10 to the 16th GeV, not too much below the current upper limit. If inflation had something to do with Petchy-Quinn symmetry breaking or supersymmetry breaking, then the energy scale of inflation could be, say, 10 to the 12th GeV, which is orders of magnitude below this upper limit, or even more. So this curve here that I draw, that gives me an optimistic outlook for LISA, actually is the largest curve consistent with COBE. So this is for the largest E inflation that's consistent with COBE. If the energy scale of inflation were lower, then this whole curve would shift down by that amount.
And so actually, with the largest inflation with COBE, I think LISA is still maybe 3 orders of magnitude away from being inverted. Oh, in omega, so that's maybe 1.5 in H.
Okay.
LISA will go to you could go to 10 to the minus 12 and the most optimistic.
Well, that's consistent. This is we've got something like, I have 25 orders of magnitude. I have 25 orders of magnitude here. And you'll see that if you come close, there's a little sliver of 10 to the minus, which is roughly about an order of magnitude. So, the other reason why this is optimistic is that I keep saying that the energy density of the universe is constant during inflation. Okay? So in the slow roll approximation, this thing doesn't move too much, and so the energy density remains constant during inflation. But if you look at a model like this, during inflation, the field is in fact rolling down the potential. So early times, the potential is going to be bigger than it is at later times. That means that at this point in inflation, the potential will be larger than at this point in inflation. That means that the amplitude of the gravitational waves that exit at this time, which are the longest wavelength gravitational waves, will have a larger amplitude than the gravitational waves that exit at later times, which are the smaller wavelength gravitational waves. So, if the inflaton potential actually does roll, which it should, then if I normalize to the upper limit due to COBE, I'll get a curve maybe that looks more like this. Okay. So this is in some sense the most optimistic estimate. And I don't think that there's any way to tilt the spectrum the other way in inflation.
So are there like 12 orders of magnitude the most optimistic and the other one?
In this one, yes. Yeah, well for this curve here, but we don't know. We honestly have no idea how close to flat this should be. It can't be too far away. It's probably not too far away from flat, but I actually don't know exactly how many orders of magnitude it can get. That's not a bad question, though. It's probably quite a few orders of magnitude, though. Because the spectral index here is n equals 0, and chances are that the spectral index does not deviate, say, more than 10% away from n equals 0, say 0.1, plus or minus 0.1, I guess one side of it. So if we take 1/10 of n, if we take n of 1/10 and then we go over 20 orders of magnitude, well, 16 or 17 orders of magnitude, this could be a few orders of magnitude.
Yeah, well, Bill just showed us how one might be able, with the Big Bang Observatory, to go to an omega of 10 to the minus 18, which in H would mean a factor of 30 below in H, below the most optimistic.
Probably not going to do with LISA.
No, not LISA.
Or I mean, or post LISA.
Post LISA.
So
Well, the other reason why, the other thing that's more urgent is just that the overall normalization is completely up for grabs. If grain unification was responsible for inflation, then we're probably not too far off. You know, we're probably within a few orders of magnitude of the right answer here. But if not, then all bets will be off. You don't want to spend your lifetime looking for this and nothing else.
Right.
I don't know, maybe you do. So, the subject of this talk is supposed to be how can you, if you can't do with Lisa, what else can you do? So, if we look at the extremely long wavelength gravitational waves, extremely low frequency gravitational waves, those gravitational waves will have wavelengths comparable to the horizon. So when we look at this cosmic microwave background, these photons scatter from a spherical surface of last scatter. So this is some spherical surface, and the photons are scattering from the plasma, the primordial plasma, on the spherical surface. Now suppose I look at a gravitational wave that has a wavelength comparable to the size of the horizon. What will happen is this gravitational wave induces motions in test masses. And the primordial plasma moves under the influence of gravity. There's nothing there to fix it in place. So the primordial plasma moves under the influence of this gravitational wave. And so this gravitational wave will induce temperature fluctuations. So say over here, the gravitational wave could squeeze things in, whereas on the other way, it would squeeze things out if we had a gravitational wave propagating in that direction. So along this direction, we would expect to see higher temperatures because the primordial plasma from which these photons last scatter is moving towards us. And so there's a Doppler shift, the bluer Doppler shift, whereas in the other direction, there'll be a redward Doppler shift. So those are the temperature fluctuations, delta T over T, that I mentioned. The problem, though, is that there are density perturbations at the surface of last scatter. There are primordial density perturbations that grow via gravitational infall to produce the large-scale structure that we see in the universe today. And we know what the amplitude of density perturbations in the universe is today because we have a lot of observations of large-scale structure. And so we know, roughly speaking, what fraction of delta T over T is due to density perturbations. And it turns out that a very substantial fraction of this temperature fluctuations have to be due to density perturbations. So if you see temperature fluctuations, you cannot ascribe them to gravitational waves. So you can't use temperature fluctuations to detect these gravitational waves. Now it turns out, though, that the motion of this primordial plasma can also induce a polarization in the cosmic microwave background. And roughly speaking, this polarization comes from anisotropic Compton scattering at the surface of last scatter. So suppose I'm a photon sitting here at the surface of last scatter, and there's a gravitational wave. This gravitational wave will induce a quadrupolar anisotropy in the flux of photons incident on this electron at the surface of last scatter. And the Thomson cross-section depends on, the Thomson cross-section, Thomson scattering can produce a polarization if the incident radiation is not isotropic. So suppose I have a photon and I have a whole bunch of radiation isotropically incident on the photon, on the electron. If the radiation incident on an electron is isotropic, then the scattered radiation will have no polarization. If, however, there is an anisotropy in the radiation, so suppose there's more radiation, say, in this direction than this direction, then the scattered radiation will be linearly polarized. Now, due to the fact that there's a gravitational wave incident on the electron at the surface of last scatter. Due to the fact there's a gravitational wave, the photon intensity incident on the electron at the surface of last scatter will be anisotropic, and therefore the scatter radiation will be polarized. So, gravitational wave produces a temperature fluctuation which produces polarization in the cosmic microwave background. Now again, primordial density perturbations will also induce anisotropies in the radiation incident on the electron at the surface of last scatter. So density perturbations, which we know have to be there, will also produce a polarization. So the existence of polarization of the cosmic microwave background cannot alone be used to tell us that they're gravitational waves. Okay? And the reason is because there's no way we wouldn't be able to tell them from the density perturbations. Now here's the good news, finally. Suppose now I measure the polarization as a function of position on the sky. Okay, so suppose I just look at that region of the sky and I measure the polarization vector as a function of position of the sky. Then I have measured a two-dimensional vector field. And a two-dimensional vector field can always be written as the gradient of some scalar field plus the curl of some other vector field. Now it turns out that to linear order in small perturbations, the density perturbations have no handedness. Density perturbations have no handedness, so they cannot produce a curl. All you can say about a density perturbation is that one region of the universe is denser than another. There's no sense of handedness that you can attribute to it. And so there's no way that you can produce a curl, because a curl necessarily requires that there be a handedness. On the other hand, gravitational waves can propagate as right or left circularly polarized waves. So a gravitational wave can have a handedness, and so a gravitational wave can produce a curl. And in fact, it does produce a curl. So the punchline is that if you measure the polarization as a function of position in the sky, with enough precision that you can look for a curl in that pattern, and you find that curl is non-zero, then you have discovered gravitational waves. Now, there is a whole lot of details, many details between this and what I'm about to tell you. Okay, one then works for a long time, there's a lot of calculations, and CMB experiments can be compared with a parameter or a quantity called the noise equivalent temperature. And just in case there's anybody who knows anything about this in the audience, strictly speaking, it's an effective noise equivalent temperature. So experimentalists talk about the noise equivalent temperature of an individual detector. But an experiment, like the Planck satellite, can be composed of a bunch of different detectors. And so you can essentially add the noise equivalent temperature of all the detectors at quadrature to get an effective noise equivalent temperature. We call this thing S, for no particular reason, little s. Little s for the Planck's, for the MAP experiment, is something like 200 microkelvin divided by square root seconds. The MAP satellite was launched about 3/4 of a year ago, and they should be announcing results at the end of this year, beginning of next year. The Planck satellite is supposed to have a detector sensitivity somewhere around 25 microkelvin square root seconds. And what people are talking about now is a post-Planck experiment that would have something like 1 microkelvin per square root second. So there's roughly, it's roughly a factor of 20, 25 jump between subsequent missions. Kobe was somewhere around 1,000 or a few thousand microkelvin root second. And the extrapolation from here to here is not completely crazy. Andrew Lang and some other people have actually been doing estimates of what you could actually do with current technology, or technology that can realistically, that you know can be developed with ideas that we have now. And so something like this is not unreasonable for a post-Planck experiment. And the current upper bound to the energy scale of inflation from Kobe is something like 3 × 10 to the 16th GeV. What we've been able to show now is that with this type of sensitivity, you could detect any energy scale of inflation greater than about 2 × 10 to the 15th GeV. And the limits come from 2 places. First of all, there is a noise. When you measure the polarization, there's going to be an error in your measure of the polarization. It comes from the existence of detector noise. And this is a measure of the detector noise. So as the detector noise decreases, your measurement of the polarization can become increasingly precise, and you can measure smaller and smaller energy scales of inflation. This is proportional to energy scale of inflation squared divided by the Planck mass. So as your sensitivity improves, you can detect smaller and smaller energy scales of inflation. Okay. The other limit that will be faced, if you were to try to go even beyond this, what I told you before about density perturbations having no handedness, that's true only in linear order and the density perturbation amplitude. If one goes to higher order and density perturbation amplitude, then there can be a curl induced. And it probably looks like that will provide a fundamental limit that does not allow you to get too much below this. This is not, shouldn't cause anybody to lose too much sleep because it's going to be quite a while until we get here. So, if there are any, 11 or 12-year-old savants in this audience, maybe they would have to worry about it. But for all of you who are comfortably into your 20s, it's probably going to be a very large fraction of your lifetime before we get down to this. So, anyway, I should say that the Planck, this should get us down to energy scales of inflation about a factor of a few below this. So Planck should detect this gravitational wave signal if the energy scale of inflation is, say, somewhere around 10 to the 16th GeV. So there is room for Planck, but to really go much below that, you'd have to go through the subsequent experiment.
So the density perturbation effects that can produce a curl, these are what?
It's a weak gravitational lensing. So what happens is if I have a polarization pattern at the surface of last scatter that has no curl, gravitational lensing deflects photon paths, and so the map that I see will have some curl induced because I've distorted the primordial map. There's a way to actually correct for that to some extent by using high order temperature correlations. And we've just finished writing a paper on that. And that's included in this estimate here.
So can you give us some references on where these numbers are computed? And
yep. So there's a paper by Kesman, Hooray, and Kamienkowski. It should appear on PRO soon. It's on Astro PH this year, earlier this year. Is it this year? It's either this year or late last year. more generally, there's a review article by me and Arthur Kozowski. That's in ANREV knuckle part side. And I can find the reference for you. If you need it, I might actually have it. No, I don't think I have it here. And there's also another paper that's by Knox and Song. It's also Astro PH 02. It's almost identical to our paper. They did the same thing independently. Exact same calculation independently and got the exact same answer. So, which is good. Which means that.
So the annual reviews paper, does that exist in electronic form?
I don't know. Well, it does. It's on Astro PH.
It is on Astro.
Yeah. Yeah. It doesn't have the weak lensing stuff in it. That was the lensing was after that.
The lensing is discussed in the Kesman curriculum.
Yeah, and you'll find references in there as well. The first paper is actually pointed out the lensing effect by Matthias Valderriaga and Laura Celiak. And here we did this calculation to see how well you could. This paper did a calculation to actually evaluate how well you could reconstruct the lensing deflection angle as a function of position in the sky to recover the primordial polarization pattern.
Any more questions?
There must be more questions. There are always questions when I talk about inflation. Huh?
Okay, we'll ask Jeff for a second. So, Jan, Ryan, and Mihai did not manage to produce solutions for this week. Their first failure in the entire course. But they promised solutions later. The problem for a particular requirement was probably the easiest problem set of the term, and that's probably why. It's so easy. So those will appear on the course